Okay, so yeah, I am the second presenter, I see. So yeah, I'll start my presentation. And my topic is back calculation of damage density of in-service asphalt using artificial intelligence-based finite element model updating. I'm Yong Deng and postdoctoral research associate at Washington State University, working with Professor Xianmin Shi. Okay, so this is the outline of my presentation. I will introduce the motivations and objective of my research, and I will briefly introduce the damage density, finite element of model updating, and I will describe the result analysis, and lastly, the summary of this research. Okay, so I will first introduce the current research on the fatigue damage characterizations. This is the direction number one of the research from laboratory to the field. And the first step for this direction is to conduct a fatigue damage test in the laboratory. There are many tests characterizing material behaviors under different fatigue modes. And next, the second step is to find the changing pattern of the material response or properties with the fatigue load. And researchers usually use analytical models with theories and criterion such as damage mechanics and fracture mechanics to describe the pattern. And the third step is to extend the model derived in the laboratory to the field. Compared with the laboratory condition, loading and environmental conditions are more complicated. Therefore, some calibration factors are included for better accuracy. Sometimes the field measurement on the fatigue damage are utilized to calibrate this model. And this is the second direction of the research. Researchers usually use the long-destructive testing devices on the pavement to measure the fatigue damage of the pavement. We can see those entity devices apply different types of load. There are stationary dynamic loads applied by the FWD, which is familiar with pavement engineers. And recently, there are two devices applying moving vehicle loads, named the rolling wheel deflectometer, which is RWD, and the traffic speed deflectometer, which is TSD. They apply moving vehicle load as traffic loads and collect the deflections of the pavement surface and use those indicators to evaluate the pavement condition. Okay, so next I will briefly introduce the motivations of this study. So the limitations of the direction number one research is the applicability, which means if any of the material types, structure, configuration, loading, and the environmental conditions is not included in the database for the model calibration, the model accuracy will be significantly affected. That's why most of the predictive models built in this way do the local calibration. Yeah, we can see this is the procedures of the local calibration in this kind of research. And this is the limitation of the direction number two research. That's the predictability of the research. And this is current research on TSD I extracted from a literature review published this year. So it shows the current research on the long-destructive testing devices on the evaluation of pavement fatigue damage. And currently, two types of research are conducted for NDT measurement. The first one is to calculate some indicators such as the structural capacity of the pavement using the device. The responses are typically the deflection or deflection slope. And the second one is the comparison between the NDT devices. People just compare indicators from different devices to check the measuring accuracy and stability. So both of these two research focus on the current condition of the pavement when the test is conducted. So using this kind of method, we have no idea the damage degree or phase of the pavement during its whole surface life. So as a result, we cannot make any appropriate and timely decisions for the pavement evaluation. So for this research, my objective is that I combine these two research directions. And first, I select the advantages of direction number 1. I use the continuous develop the continuous development model, and I involved some material and structural damage mechanism. And I also used advantages of research number 2. The first advantage is the individual section-based measurement. So if you want to evaluate any payment sections, you can just conduct entity test on that payment section. And the second is that using this kind of method, there is no additional damage to the payment. We don't have to extract codes from the field payment to do any laboratory test. So I combine these two research directions to make predictions of fatigue damage development. Okay, next I will briefly introduce what is damage density used in this study. So in the fracture mechanics, when damaged material is under external load, its stress and strain state can be separated into 2 categories. The first one is the apparent stress and strain, which are defined in the apparent or damaged configuration of the material. They are the terms measured in the laboratory or field. The second one is the effective stress and strains that are defined in the effective or undamaged configuration of the material. They are the terms we usually see in the textbooks. And those are the terms used in most constitutive models defined for undamaged materials. And the last, I used the damage density to combine them. Okay, this is the stress-strain relation of viscoelastic materials derived from the Hooke's law. If we introduce the damage density into this equation, we can just re-express the stress-strain relation of the viscoelastic material using generalized Maxwell model. So we observe this equation, we can find 2 points. The first one is that word terms are the apparent ones, which means those stress and strains can be measured in the field or in the laboratory. And the second is that I implement the damage density into this theoretical model of the viscoelastic material. Okay, so next I will introduce the non-destructive test applied in this study. I used the FWD test for the NDT test. So the FWD test measures the payment responses under stationary dynamic loads. FWD drops a loading plate from a certain height to the pavement surface, and the vertical deflections of the pavement surface are measured by the sensors mounted along the center line of the load. And I built a two-dimensional axis-metric model in the flat element software console multiphysics to represent the pavement structure of interest in the FWD test. 2D axis-metric model was approved to balance the accuracy and the simplicity to simulate the FWD test. For example, we can build the test, apply the load, and extract payment responses from the finite element model. This is a typical deflection response of the pavement surface of asphalt pavement surface. Okay, next I will introduce what is model updating. So in this study, so I will introduce step by step. The first step is to determine what model parameters should be updated in this study. So for typical model updating, it can be the material or structural properties, boundary conditions, and something like that. And in this study, we want to update the damage density and the supporting layer modulus. Next, we build pavement FE model, and we extracted the pavement responses from the FE model in this study, which are the deflection magnitude at sensor locations. And we compare the predictive responses with the measured ones from the field. Since we didn't know at first that what is the right damage density is, so the comparison for the first comparison is definitely no. Next, we will go back to the first step. We should adjust the model parameters to be calibrated until the predicted and measured responses match with each other. So the last questions for this flow is how to update model parameters for the next iteration. We cannot just randomly guess until the responses match with each other. We have to find a way to automatically and intelligently update the model parameters. So I used AI algorithms in this study to automatically and intelligently update the model parameters. I used the particle swarm optimization, which is PSO. It is an evolutionary algorithm for optimization problems. So candidate solutions are simulated as individual organisms in a swarm. They are updated based on the current and historical performance of itself and other solutions. So basically, we simulated each potential solutions as an individual particle. This particle has its original direction for the next step, but this particle will communicate with local best particle, which is calculated by the previous performance of this particle. It will communicate with another particle, which is the global best particle. It is calculated by the previous performance of the group, which is the swarm. Finally, it decided not to go the original way. It updates its way based on the global best particle and the local best particle. So that's the mechanism of the PSO. And I also use the LTPP database to extract the basic information of the payment section. So in the LTPP database, there are more than 2,500 payment sections in North America. And we can extract the payment structure and the materials information, climate, traffic, and long-destructive testing information from this database. So for this study, I used the payment structure information, climate information, which is mainly the temperature, and non-destructive testing information to build the FE model. Okay, so let's record the flow of this study. So in the vertical directions, I build FE model and do the model updating so we can calculate the material properties of the payment at a fixed time. In the horizontal directions, when we calibrate material properties at different time points, we can obtain the material deterioration with the surface time. So that's the flow of this study. Okay, this is the damage density development I obtained from this study in 5 sections. Based on the available data, I obtained the damage density development with surface time of 5 sections from 3 different states. We can see the damage density development has different patterns. Okay, so in this plots, we separate the damage density development curve into 2 distinctive patterns and focus on its relationship with the thickness of the asphalt layer of the pavement. So the first one is a 3-stage curve of which the curvature changes from the negative to positive. And the second one has 2 stages of which the curvature approaches to 0. We found the type 1 functions works for pavement with relatively thin asphalt layers, and the type 2 functions works for pavement with thick asphalt layers. In the previous study, the loading mode of the laboratory fatigue test is selected by the asphalt layer thickness, and the threshold is 127 millimeter. So it is possible that the damage density development in pavement follows this criterion as well. Okay, these 2 figures show the damage density versus the alligator cracking volume. So I calculate the alligator cracking volume instead of the alligator cracking areas recorded in the LTPP database. I multiply these terms with the AC layer thickness. The AC layer thickness was considered for 2 reasons. The first one is that the alligator cracking is penetrating cracking from the layer bottom to the surface. So when we see the alligator cracking, it means the whole asphalt layers has this kind of cracks. And the second one is that the damage density development is potentially affected by the asphalt layer thickness as indicated in the last slide. So the linear relationships between the damage density and the alligator cracking volume can be found in both figures, which are the result from two states. So these two figures tell us a potential linear relationship exists between the fatigue damage properties of the material and the fatigue damage performance of the pavement. And this relationship only relies on the material type since the same materials were utilized in one state. Okay. Okay, I'll summarize the findings and the highlights of this study. The highlights number one is we implemented damage density in pavement models to evaluate fatigue damage of the pavement. And the second highlight is we used the AI-based FE model updating for pavement parameter calibration. And highlights number three is that we develop damage density development in damage performance determination. So the findings of this research, number one is we compare the damage density development versus the AC layer thickness. We can see the AC layer thickness control the damage density development pattern. And finding number two is we draw the damage density versus alligator cracking volume. And we find a potential linear relationship between the damage density and alligator cracking volume, which is controlled by the material type. So this study shows a promising application of the damage density in the evaluation and the prediction of the fatigue damage of asphalt pavement, which will lead to a timely and cost-effective pavement maintenance and rehabilitation. Okay, so the contributors of this study are the Professor Luo Shi from Zhejiang University in China and her PhD student Wang Hang, and I will also attach the email address of these two researchers. And if you have any detailed questions, you can email them or directly email me. I'm very willing to answer any questions. And also, the details of this research are included in the published paper in the journal Fatigue and Fracture of Engineering Mechanics of Structures. And I will also attach the DOI of this paper, and you can just find it online. And welcome to discuss any questions if you have. Okay, this is the presentation of my research. Thank you for your listening.